Hi everyone, welcome to my channel. In this video, we are going to talk about the step-by-step approach using which you can design your own relay driver circuit using a BJT, or which we also call commonly as transistor. The requirement at hand right now is that I have a Raspberry Pi using which I want to drive a relay. Now, those who are familiar with electronics will immediately be able to conclude that it's not possible to directly hook up a Raspberry Pi with the relay. Reason is that the current requirements of relay are much higher than what the Raspberry Pi can deliver. Now to mitigate this, we usually come up with a relay driver circuitry which takes care of the maximum amount of current which the RPi or Arduino or any microcontroller for that matter can handle. And then it allows the relay to draw a higher amount of current which is required by the relay to function properly. So the relay driver acts as a bridge between these two devices, and basically it allows a low power device, which in this case is the RPi or could be Arduino, to drive a higher power device, which in this case is a relay. But the same circuit can also be used to drive other loads like the motors or maybe lamps, bigger lamps, right, which have higher current requirement. Uh, Now I'll be describing how to design this circuit and what all constraints or parameters that we have to keep in mind. So moving on, this is the schematic that I will be using. Here we have this transistor. This is the NPN BJT in this case. Then we have a base resistor attached to its base. We have the input signal represented by Vin over here. IB is the current that's flowing into the base. Then we have the supply voltage, which is VCC. Here is the load, the relay in this case, which is connected to the collector terminal of the BJT, and the emitter terminal is connected to ground. As you can see that the current which will be flowing through the relay will also be going to enter into the collector terminal. That's why I'm representing it with IL, which stands with load current, and also IC, which is the collector current. In this case, both of them will be equal. Now there is also a diode which is reverse biased. This diode is called as a freewheeling diode, and why it is used is something that I will be describing as we will proceed ahead. So now let's do a quick math around the schematic to understand the values of the various component that would be required. Now to begin with, we'll have to firstly understand what kind of a relay we are having, right? So as I mentioned that in this case, the supply voltage is going to be 12 volts, right? Because the relay that I have is also going to be, it also works at 12 volts. Now, experimentally, I will be determining the current that this relay would be drawing, right? So this is one variable that needs to be figured out. Then the BJT in this case, we will be running this BJT in the saturation mode. Saturation mode basically would mean that the voltage between the collector and the emitter would be around 0 volts. So, in other words, the transistor will act like a short from collector to emitter. This also means that the entire supply voltage will be present across the relay, and the relay will be able to draw a good amount of current provided the BJT is supporting it. Right. So, yeah. And now to put a transistor into saturation region, what we need to ensure is that the base emitter junction is forward biased, right? Now, in this, like as we'll be proceeding ahead, I'll be using the BC547 as the transistor, right? And for it, the forward bias voltage is 0.7 volt since it's a silicon-based semiconductor. All right, so now again looking onto this part of the circuit, let's write the voltage current equation. So it will turn out to be Vin minus base current multiplied by base resistance equals to VBE which, as I mentioned above, is going to be 0.7 volt because we want the transistor to be into the saturation region. Now, saturation region basically implies that whatever charge carriers are present inside of this transistor, all of them will be playing a role in handling the collector current or the load current, right? Okay. Now, if I could quickly reshuffle this equation, because we need to find out the value of RV, so the equation will become Vn minus VBE over IB, right? So this will allow us to compute the base resistance that will be required in the circuit. Now, the other unknown in this equation is the base current. How do we find it? So as I'm saying that, we will be operating this transistor in a saturation region. So just before a transistor enters into a saturation region, this equation holds true. I mean, this is at the borderline of the active region and the saturation region. Right. So to ensure that the transistor goes into the saturation region, we'll have to, I mean, this equation will hold valid when the base current is when the base emitter voltage is 0.7 volt. So this is the third, I would say, equation, and also as we have already discussed, that collector current in this case will be equal to the load current. So as we move ahead, what we will be doing is we'll take the relay, identify or experimentally retrieve the operating current of that relay when we supply it with the 12-volt supply, which will give us the collector value. Then we will take the transistor and we will experimentally we will again determine its beta, which is the current gain of the transistor. Using the multimeter, it is possible to measure it. We can also refer to the data sheet to get a range of the values, so that we design a circuit that is more fault tolerant. So once we have the collector current and the gain available, we can use it to compute the base current. And once we have the base current, we can substitute the base current in this equation to get the base resistance value. Now, since in this case, as like I mentioned, that I'm going to use a Raspberry Pi, so the V in that I will be getting from the Raspberry Pi would be 3.3 volt, right? So using all these values, we will be able to uh, compute the value of the base resistor. So let's move ahead and let's get to the workbench where we'll do the measurements and then we'll try to come up with the circuit. Okay, so as you can see, the multimeter right now it's showing the supply voltage with which I will be working. This is the relay that I will be using, and these are the two coil terminals of it. These two. So the first thing that I need to do here is to calculate the load current, which basically is the current which this relay will be drawing when it is energized. So let me quickly flip my multimeter into the current mode and make the required connections. Now I have wired the relay in such a manner that the multimeter is in series with the relay. Now if I touch the probe, the relay has clicked and we can see that it's drawing around 66 milliamps of current. I'll repeat it. Okay, so with that being said, that basically implies that the I collector or the I load here is going to be 66 milliamps, right? Now, what I'm also additionally going to do is measure the gain of the transistor. So this is the BC547. I'm not sure whether it will be visible. This is the BC547 transistor that I'm having. Now, as per the pinout, uh, the collector, base, and emitter pins are like this for this transistor, right? So in my multimeter, I'm going to insert the NPN transistor in this fashion so that the pins are aligned with its pinout, and I'm going to move the multimeter into the HFE mode so as to measure the gain of this transistor. So the beta here comes up to be around 320, right? So we have these values. Now what we need to do is find out the base current that's required. So as we had seen earlier, the base current would be given by this, which in this case is going to be 66 milliamps divided by 320, and this will come out to be 206 microamperes. Now from the other equation that we had, Vn minus 0.7 divided by Ib would give me the value of the base resistor. Now Vin, as I mentioned, since it's a Raspberry Pi, it's going to be 3.3. So I'll quickly simplify it. 3.3 minus 0.7 divided by the base current that we have here. It is 206 micro amps. And if I complete this math around it, this will come out to be around 12.6 k kilo ohms. So this is the base resistance that we need to put in here in this particular circuit. Right, this is the schematic that we have seen earlier. This is our freewheel diode. This is 3.3, this is 12 volts, and now RB we have determined it to be around 12K, right? And this should be sufficient to drive a transistor into this BC547 transistor into the saturation mode, and then we should be having a working relay as and when we provide 3.3 volts to the input terminal over here. So now let me build this circuit really quickly on the breadboard, and then we will test it. So now the circuit is all prepared, and it's on the breadboard. I have this transistor, right? The leftmost terminal is the collector, then followed by base, and then the emitter. So emitter is connected to ground, base is connected to this 12K resistor, which is then connected to this wire, which will be getting in the 3.3 volts of signal. The collector is connected to relay. The other end of collector is connected to this freewheeling diode. The other end of this freewheeling diode connects to the supply rail, which is 12 volt, and 12 volt is also fed into this relay. Now the expectation is that as soon as I provide a 3.3 volt signal to the base of the transistor or to the input of the circuit, the relay should click. Now what I also am doing here is I will be providing this input to the circuit through the multimeter, because I would like to measure the current that will actually be flowing into the base. So now I am going to connect the one probe of my multimeter to the input signal, and the other is going to end up into the 3.3 volt. Now if the circuit will work, we should hear the relay clicking. Let's see. It is working. We can see that the base is drawing around 0.18 microamps, milliamps, sorry, whereas we computed it to be around 206 microamps, which is nothing but 0.2 milliamps, so pretty close. And the relay is working. Now let's also measure the collector current to see how the circuit is behaving. What I'll do is I'll connect my black probe so that we have the correct polarity of the current, and okay, I'll turn the circuit on first, and then now I'm going to connect this probe over here. Sorry. So it's 53 milliamps that the relay is able to draw right now, which is less than what it was drawing earlier. Probably what we can try to do is to try and reduce the value of the base resistor to see if we get a higher current. Let's do that. So I'll probably be setting up a 10K resistor here instead of 12K, and then we will see how the behavior of the circuit changes. So now with the 10K resistor, let me quickly check the current that the circuit is that the relay is drawing. So it's around 55 milliamps. right? So a little bit of improvement, but not that much, probably because the transistor is now entering into the saturation region. And once it is saturated, it's not that easy, or I should rather say that once it's saturated, it's not possible to increase the current any further, the collector current, right? So now let me quickly also verify whether once the transistor is turned on, whether the relay is closing or not, right? So for that, I'll take my multimeter into continuity mode, test it once, and let's see if we are getting a continuity, and we are getting, right? So the relay is closing. If I remove this supply voltage, then the other two terminals should become continuous, right? So this shows that the relay is working. So we have successfully built the relay driver circuit by having an amalgamation of theory and practical. I hope you liked the video, and let me know your views in the comments. And please like, share, and subscribe. That will help me to grow my channel. Thank you so much for watching. Bye. The purpose we have this freewheeling diode is that, whenever the relay is turned on, the current will be flowing in this direction. Relay is basically an inductor. So when the supply of the current is stopped, because let's say the transistor turns off, in that case, this current cannot immediately die. It needs some path to continue flowing. And if you break that path, it will result in a buildup of a very high voltage across the relay terminal, which can then damage this transistor. So to prevent that from happening, we insert a freewheeling diode, which as soon as the load current tries to stop, the resulting voltage that is induced in this relay, tries to keep that current flowing via this freewheeling diode. The diode gets forward bias immediately when the magnetic field starts to collapse, and the current can then uh, you know enter into a loop and keep on flowing until it dies due to the losses in the circuit. So this, and that is why this diode is called as a freewheeling diode.